Welcome back to another lesson in MCV4U. Today we'll be talking about the derivative of y is equal to sine x and y is equal to cos x. Start off with the warm-up question. It says here to differentiate y is equal to x to the power of x. You may start and you may think about using the standard power rule to differentiate this question. So you may think y prime is equal to, bring the x down, you have x times x to the power of n minus 1, so x minus 1. In this situation, this idea of the power rule does not work because there is a variable in both the base and the exponent. So here, n times x n minus 1 does not work because the n value in this situation an, is not an actual value, rather it is an exponent. So here, it is not applicable in this case. Again, because there's a variable as base and exponent. Okay, so if we're not able to differentiate that way, we have to think about how to solve for this particular problem. So the first thing that we can do here is we'll find the natural log, or take the natural log of both sides. So here we have ln y is equal to ln x to the power of x. And here we see that we can bring the x to the front. So here we'll have ln y is equal to x times ln x. Here we can find that y will be equal to e to the power of x ln x. We find the derivative of I prime. We see that we have e to the power of x ln x. So remember, e to the power of anything here, again, stays the same. And then we're going to have to derive the inside. And so deriving the inside, use product rule. You have ln x plus x times the derivative of ln x, which is 1 over x. And here we understood, again, that y was equal to x to the e to the power of x ln x. So if we look at this here, we know that y is also equal to x to the power of x. So here we can rewrite this as y prime is equal to e to the power of ln x to the power of x times ln x plus 1. So that's, again, e to the power of ln x to the power of x times ln x plus 1. So here we know that e to the power of ln x will simply just give us x. So here we can rewrite this as y prime is equal to x to the power of x times ln x plus 1. And if we move in, we'll get x to the power, we'll get x to the power of x ln x plus x to the power of x. Okay, and there's another way to solve this as well. So the second option, or option 2, is to use implicit differentiation. And so here, if we start off again with our natural log of both sides, so we have ln y is equal to x ln x. So here, if we derive this, we have 1 over y times y prime, or dy over dx, is equal to ln x plus x times 1 over x. And here, if we multiply everything by y, so multiply everything by y, here we have, let's just rewrite this, we have 1 over y times y prime is equal to ln x plus 1. And if we multiply here, again, everything by y, then we'll be left here with y prime is equal to y ln x plus 1. Here we know that y is equal to x to the power of x, so we can replace that. So y prime is equal to x to the power of x ln x plus 2, which is the same as the derivative we found using the first option. Okay, so let's move on to the things we're looking at today. So here it says graph y is equal to sine x and y is equal to cos x on the given grids. And then tells us to estimate the instantaneous rate of change of each function for the given values of x. Plot the points that represent the instantaneous rate of change on the same grid as the graphs y is equal to sine x and y is equal to cos x, and then connect the points with a smooth curve. Okay, so here, let's start with the graph of y is equal to sine x. And I'll underline kind of which color that I'm using here. So here we'll have label 1 and -1. And we'll label these as pi over 2, pi, 3 pi over 2, and then finally here, 2 pi. Okay, and we know here for the graph of y is equal to sine x, we know that at 0, the zeros are at 0, pi, and 2 pi. We know that at y is equal to sine x, that's maximum at 1 at pi over 2, and then a minimum at -1 at 3 pi over 2. So here, if we graph this, it's at 0, goes to 1, goes back down. It's a minimum at 3 pi over 2, and then continues to 2 pi. And here we'll graph the y is equal to cos x. So here we'll do this in, let's say, red. So y is equal to cos x. So we'll label this again at this bottom graph here. So we'll have, again, 1, and -1, and we have pi over 2, pi over 2, pi, 3 pi over 2, and 2 pi. And so here, for the cosine, graph. And we know that our zeros are at pi over 2 and 3 pi over 2. And we have maximum at 0 and 2 pi at 1, and then a minimum at pi at -1. So here, if we graph this, starts at 1, hits a 0 at pi over 2, it's the minimum at pi, goes back to a 0 at 3 pi over 2, then hits and that maximum here at 2 pi, and it continues on as you go through the different cycles. I want to look at the derivative of the graph of sine x. So again, when we're looking and we're thinking about the derivative, remember the derivative is also the slope of the tangent. And when we're looking at it in terms of the entire sine graph, it's going to be the slopes of the tangent at all the different points of the sine graph. And so if we just zoom in here and we try to draw some tangent lines here, again, what we are going to see when we look at the graph is we're going to graph all the different slopes of the tangent at the different points for the sine graph. So if I bring your attention to the left side of the screen, here I have a graph of y is equal to sine x in the dotted green line. And the red line shows the slope of the tangent at a specific point. And then the purple will be graphing all the points of the slopes of the tangent, which will also show us the derivative of sine x, or the derivative function of sine x. So here we see that at 0, or x is equal to 0, we see that the value is 1. And remember, the y value here will help represent the slope of the tangent, which is the derivative at this particular point. So at 0, our slope of the tangent is 1. And we notice that the slopes of the tangent, so if I just play this for a little bit, the slopes of a tangent are all positive between 0 and pi over 2, and which means that our graph will be above the x-axis, or our derivative graph will be above the x-axis. Then we'll eventually get to pi over 2 around here. When we get to pi over 2, we see that there's going to be that local maximum, and at that local maximum, we have a horizontal line, and which means that our slope will be equal to 0. And then as we go from pi over 2 to pi, we see that the slope of the tangents will start to be negative, which means that, again, our graph of the derivative will be below the x-axis. So here we see that now it's below the x-axis, and it'll continue and continue until we hit a specific point. Again, hit the specific point where again it starts to increase again after it hits the local minimum, again where the slope is 0, and then it continues up all the way to 2 pi, which will stop it there. And then at 2 pi, again, it hits that value of 1. So here, if we go back to our notes, so can we see from that animation, again, that in this animation, we can see again where the values of the tangents will be at different points of the sine x graph. And so we see here that at x is equal to 0, we saw that the slope of the tangent was at 1, and the same thing when we get to 2 pi. What we noticed as well is when we got to pi over 2 and 3 pi over 2, we saw that there was a horizontal line, again, which means that the slope of the tangent was 0, which means that the derivatives here would also be 0. And then we saw that when we reached the local minimum at the value of pi, we saw that it hit the point of -1. So we see here when we're looking at these particular graphs, again, it hits at different points at 1, 0, negative, and -1. And so if you notice what is occurring here, if you compare with the other things we wrote on this chart so far, if you notice that the derivative of sine x is the same as cosx. So actually, if we graph that, so we have 1, 0, -1, 0, and 1. So you notice here that the derivative of sine x is the same as cosx. So if we look at our conclusion here, in this box, we see that f of x is equal to sine x, then f prime of x is equal to cos x. And so here, now we have to investigate. If f of x is equal to sine x, then f prime of x is equal to cos x. Does that mean f of x equals cos x will have the derivative of sine x? So let's take a look. So let's take a look again at the screen on the left. And so we'll go back to 0. So we see here, to start, again, the cos x graph is in the orange dots. The graph of the derivative will be in blue, and then the tangent lines will be in green here. So we see at 0, at x is equal to 0, again, there is a local maximum there. And for that local maximum, again, it is a horizontal line, which starts at 0. And we see that in this situation, the tangents actually start with a negative slope. So they start off with a negative slope, and then they'll hit a point where they'll start to become positive again after it hits the local minimum. And it keeps going until it gets to the value of 2 pi. Value of 2 pi here. And so again, what we'll notice here is that it starts again at 0. It goes down, eventually hits when it hits the local minimum. Again, then the slopes will change from negative to positive, and then it'll hit again the other local maximum, and then again that will be at a value of 1. And so now if we fill in our graph here, so we fill in our graph here, again for the derivative of cosx, we see that again at 0, it started actually at 0. And then when it went to pi over 2, so if we look at the graph, when it went to pi over 2, and at pi over 2, it was at -1. At pi, it was at 0. 3 pi over 2, it was at 1. And then finally at 2 pi, then at the end, it ends at 0, as you can see there. And so here, if we graph this, so it starts at 0, and -1, then back to 0, then 1, and 2 pi. So again, we wanted to see again if f of x was equal to cos x, if f prime of x was equal to sine x, because we saw that f of x is equal to sine x, then f prime of x is equal to cos x. However, if we compare these values of sine x and the derivative of cos x, we see that the zeros are the same, but the maximum and minimums are flipped, which means that here, if f of x is equal to cos x, then f prime of x is actually equal to negative sine x. So here, it's actually equal to negative sine x. So here, now, if f of x is equal to sine of g of x, then f prime of x is equal to cos g of x, and then the derivative of the inside, so multiplied by g prime of x. And if cos g of g of x, then f prime of x is equal sine, to negative sine g of x times g prime of x. Okay, so let's look at a few of these examples. So here it tells us to differentiate the following. So again, we have y is equal to cos of 3x squared. And so again, this is the outside, so derive the outside, and then we'll derive the inside, which is 3x squared. So here we have y prime. So y prime is equal to the derivative outside. So the derivative of cos is negative sine. So we have negative sine 3x squared. And then the derivative of the inside, which is 6x. Okay, let's look at the second question here. So we have g of x is equal to square root sine x. So again, the outside in this situation, so the outside is square root x, or the square root, and then the inside is sine x. Remember, and when we have the derivative of the square root, it's 1 over 2 square root of whatever value's inside. So just a reminder there, and that's what we'll use for this particular question. Here we have g prime of x is equal to 1 over 2 square root sine x, and then multiplied by the derivative of the inside, which is the derivative of sine x, which is just cos x. And so that's equal to cos x over 2 square root sine x. Okay, so now this third problem. So it says h of x is equal to 3x squared minus 4x times cos 2x. So here we're going to use the product rule. So 3x squared minus 4x will be our a, and cos 2x will be our b. And so our product rule, remember, is a prime times b plus a times b prime. So here we have h prime of x is equal to, first do a prime, which will be 6x minus 4, and we'll keep the b value, which is just cos 2x. And we'll add, so a here is 3x squared minus 4x, and then the derivative of b here will be negative sine 2x, and then the derivative of the inside there, which is 2. Okay, so let's look at this last question here. So here it says y is equal to sine of 5x. So that will be our a value here. And we have cos squared of x squared plus 1. And that will be our b value here. So then we're using the product rule. So we have a and we have b. So here, y prime is equal. So keep a by itself. So we find the derivative of a. So we have 5. So we'll have 5 times cos 5x. So again, the derivative of sine is just cos x and then multiplied by the inside, which is 5x. So 5 cos x times cos squared x squared plus 1 plus, now we have to find the derivative. So we have sine 5x. And then here, cos squared x squared plus 1. So cos squared, this part is considered the outside, and then we have to derive the inside. Okay, we get multiplied by 2 cos x squared plus 1. And then we also have to multiply by the inside. So the inside is considered, again, cos, cos x squared plus 1. So here we have minus sine squared plus 1. And then we have to derive the inside again. So the inside of x squared plus 1, which is 2x. So here again it says example number 2. So again, find the equation of the line at the tangent of the curve y is equal to sine x plus pi over 2 at the point on the curve where x is equal to negative pi over 4. So here we have y is equal to mx plus b. That's what we're trying to find. Again, the equation of the line. We know that the slope, again, is equal to the derivative, or y prime. So the first thing we want to do here, again, we want to find the corresponding point for y for negative pi over 4. So here, if we find our derivative, so we have y prime is equal to cos x plus pi over 2 times the derivative inside, which is just 1. Here we know that our slope is equal to y prime, and we know that that's when x is equal to negative pi over 4. So if we sub that into our equation, we have cos negative pi over 4 plus pi over 2, which is equal to cos pi over 4, which is equal to 1 over square root 2. Here, we know that point that we have is at negative pi over 4 and 1 over square root 2. And if we set that back to the original equation, we have y is equal to sine negative pi over 4 plus pi over 2. Here we get y is equal to sine pi over 2, or sorry, sine pi over 4. So then y is equal to 1 over square root 2. So here we're going to set that back into our equation of y is equal to mx plus b. So here we know that our slope is equal to 1 over square root 2. And we know that a point that we're going to be able to sub in is negative pi over 4 and 1 over square root 2. Here we have 1 over square root 2 is equal to 1 over square root 2 times negative pi over 4 plus b. So I have 1 over square root 2 is equal to negative pi over 4 square root 2 plus b. Here we see that b is equal to 1 over 4 square root 2 1 over square root 2 plus pi over 4 square root 2. Here we're going to get the common denominator of 4 square root 2, so we'll multiply 1 over square root 2 by 4. So our b value here is equal to pi plus 4 over 4 square root 2. So our equation, therefore, is equal. So y is equal 1 over square root 2 x plus pi plus 4 over 4 square root